Good evening. My name is Rebecca Walker, and I'm a student in Dr. Gilchrist's academic cooperative course within the chemistry department. I spent this semester researching and performing experiments concerning the effect of humidity on the thermal decomposition of acetylsalicylic acid, better known as aspirin or ASA. Aspirin works as an analgesic, antipyretic, and anti-inflammatory drug. It's also commonly prescribed for daily use to reduce the risk of blood clot, stroke, and heart attack. As someone who's pursuing medicine, I wanted my project to be related to the field. There's a good amount of academic literature concerning the thermal decomposition of ASA. The paper that I'm mostly focused on spoke about the kinetics and mechanism of anhydrous thermal decomposition of ASA. This study confirmed that decomposition occurs in two steps, which you can see here and here on this thermogravimetric analysis curve. The paper also suggested that decomposition products form linear oligomers that eventually become cyclic oligomers, which can be seen in the image on the right. I found additional papers studying the behavior of ASA in the presence of humidity. After extensive research, I was able to come up with my project, which was different from anything I'd read so far. Storage parameters set by the FDA state that aspirin is to be stored in a dry, cool environment between 15 and 30 degrees Celsius. Effectiveness of drugs can decrease with decomposition and potentially form harmful products. Results of this experiment could be applied to storage indications for over-the-counter aspirin in unfavorable environments such as a hot vehicle or humid bathroom, or could be applied to formal assessment of pharmaceuticals. ASA hydrolyzes into salicylic acid and acetic acid. Heat also contributes to decomposition. To investigate products under these conditions, samples of ASA were placed in a lab oven for 30 minutes at 80, 140, 150, and 180 degrees Celsius. These temperatures were chosen based on potential conditions in a hot vehicle, melting point of ASA, decomposition temperature of ASA, and boiling point of ASA, respectively. Fresh samples were heated under the same parameters but in a humid environment. This was achieved by placing a saturated sodium chloride solution in the oven. Proton, NMR, and IR spectra of each product were generated. Proton nuclear magnetic resonance spectroscopy measures the magnetic frequency at which a hydrogen resonates. Appearance of peaks in the spectrum depend on the environment surrounding the proton. Infrared spectroscopy is the analysis of infrared light interacting with a molecule. IR spec measures vibrations of atoms. Using these measurements, it's possible to determine the functional groups of a molecule. Functional groups absorb infrared radiation, which is reflected as a peak on the IR spectrum. I collected NMR and IR data on salicylic acid, 2-carboxyphenyl salicylate, and ASA to have baseline spectra to compare my products to. I also analyzed the products with thin layer chromatography, a method for separating components of a mixture. Because NMR and IR provided more detailed data, I decided to exclude TLC findings from my results. The IR spectra provided the most information about the decomposition products. Comparing both samples at 80 degrees, the significant carbonyl peaks are identical to those of untreated ASA. This confirms that ASA does not decompose at 80 degrees in dry or humid environments. At 140 degrees, the dry sample remained unchanged, but the humid sample began to decompose to form dimers and anhydrides. These carbonyl groups then appear in the dry sample at 150 degrees. By 180 degrees, the humid sample has evaporated and the dry sample only shows one significant peak. The peak at 1690 was unable to be identified using collected reference data and known frequencies, but it's likely a dimer or aromatic substance. Here you can see under what conditions the peak appeared. Proton NMR spectroscopy showed the aromatic region becoming less resolved as the temperature increased, indicating multiple aromatic compounds as products. This can be seen here when comparing the spectrum at 80 degrees versus 180 in the chemical shift region of 6 to 7.5. Another finding with increased temperature is a shoulder coming off the downfilled methyl group. This could be an anhydride associated with the aromatic mixture, which would also explain decreasing resolution. There's potentially more NMR data of significance. Proton NMR data would have been quantitative with the addition of a substance to use for integration. Quick carbon-13 NMR scans could be performed on the products, but require a much longer scan of multiple hours. Aspirin left in a hot vehicle or stored in a humid bathroom for a short period of time should not decompose or lose effectiveness. Since the samples in this experiment were only heated for 30 minutes, I cannot say if aspirin maintains its structure in a hot vehicle or a humid bathroom for longer periods of time. I predict over a long period of time, maybe years, aspirin would decompose. Thank you for listening to my presentation. I hope you enjoyed.